buffered solutions. Also known as buffers. So, I don't know if you've ever really heard that word in general language before, but if someone's acting as a buffer, they're kind of like keeping one thing from getting to another sometimes, right? Or something like that. In a buffered solution, basically what it is, it resists change in pH. So you add acid to a solution, it doesn't necessarily change the pH to make it very much more acidic. It will change it a little bit, but not much. Or if you add a base, it's not going to change the solution to make it very much more basic. Okay? So these are very useful. The book, and I will tell you just one little hint on your research paper, there's a section in 17.2 in the book that I said in the reading guide is not optional, it's required. What that means is I might ask a test question about it because it's in the AP curriculum about blood as a buffer system. Okay, so blood in your body is actually a buffer that resists drastic changes in pH, and that's a good thing because if it didn't, then we would kind of be in some trouble because our body, you know, a lot of the chemicals in our body need a very specific pH range in order to be able to operate effectively. So if blood did not have a buffering action to it, then we could be in big trouble if additional acid or additional base was added into our system. So human blood, seawater, and notice they have different pHs. That all depends on the ratio of the acid to the base, okay, in the buffer. I'm hoping these notes work because it's been 2 years since I've changed these. We'll see. So I'll just follow along in the book to make sure that I'm not missing anything that the book now talks about. Where am I? This is going to be a great video, I can tell already. Okay, so a buffer has a weak acid to neutralize OH minus, and it has a weak base that will neutralize the H plus. Okay, the weak acid and the weak base need to not react with each other in order for this to work. So usually we use conjugate acid-base pairs. That's kind of the best way to prepare a buffer. You guys are actually going to do this in a lab at the end of the week. You're going to make a buffer solution with a certain pH, and it's going to have to resist change in pH when we add acid and base into it. So that should be kind of fun. So a lot of times what we'll do is by mixing a weak acid or base with a salt of that acid or base. So I'll show you some examples of this. Okay, so an example here, how could we make a buffer solution out of a solution that contains acetic acid? Okay, so we've got acetic acid in the solution. What would make that solution a good, well, first of all, is it a good buffer solution at this point? If I just have acetic acid in it. So if I have acetic acid in there, what happens if I add a base? Can the acid neutralize the base? Yeah. But if I have just acetic acid in there, what happens if I add acid? Yeah, it's just going to get more acidic. It can't resist the change in pH because there's no base there, right? So just the acid by itself is not a good buffer. But what could I add into this to make it a good buffer? If I've got acetic acid. So acetic acid, HC2H3O2. What might be something good to add into there to make it into a good buffer solution? C2H3O2 minus acetate. Okay, now I'm normally not just going to add acetate ion into a solution, right? What would I probably add into the solution? It's going to be some sort of salt. Yeah, sodium's a good one, usually, because sodium doesn't do anything, right? So sodium, if I added sodium acetate, as soon as that goes into water, it dissociates. Now I have Na+, which does nothing to the pH of the solution. And then I've got C2H3O2-, which would be the conjugate base of this acid. So now we've got a good buffer solution, right? So now we've got the acid that can react with any base that we put in. And then we've got the base over here that can react with any acid that we put in. Now, it's only going to resist a pH change up to a certain point. Okay? Eventually, you add enough acid, strong acid or strong base, and you're going to change the pH. But for a while, it can resist a pH change. Okay, so how could we make a buffer solution out of a solution that contains ammonia? Ammonia is NH3, right? What is NH3? What kind of chemical is that? It's a base, right? A weak base, okay? So then I would need its conjugate acid in the solution, which, what is its conjugate acid? Say it again. Ammonium, NH4+, right? Now again, we're probably not just going to add the ammonium ion into the solution. We would add a salt that would give us the ammonium ion. Can you think of an example of a salt that would work here? Well, okay, we can't put it with sodium this time, right? Because then you would have two positively charged things. We need an anion. Yeah, chloride would work because chloride is the anion of a, it's the conjugate base of a strong acid, so it's not going to affect the pH of the solution at all. So NH4Cl, ammonium chloride, would be a good one to put into that solution, and that would make us a good buffer. Okay? General equation for a buffer, where you've got a weak acid and one of its salts. So the equation would be, that's weird. I don't know why it's doing that. All my lines are wavy now. HX in equilibrium with H plus X minus. Okay? So there's your general equation. Here's our acid. Here's our conjugate base. And the Ka expression for this equation is Ka is equal to H plus times X minus. You know what? I'm just realizing this is a derivation of Henderson-Hasselbalch, which you don't really need to know. I'll just rush through this very quickly, okay? So if we solve this equation for the H plus, you know what? I don't think I have time for this because this is not something you need to know for the AP exam. So if you guys get out your equation sheets, if you have those with you, you will see the Henderson-Hasselbalch equation, okay? Let's see if I have it on here. Nope. Okay. It's going to be pH equals pKa plus the log of the base concentration over the acid concentration. You guys see that equation on there? Is that how they write it, base over acid? Oh, they do the A minus over the HA. Okay, so another way you can write the base is, you know, the general form of a base is A minus, and then the general form of the acid is HA. So you just need to know what that actually means, okay? So there's your equation, Henderson-Hasselbalch, and this is a really important equation for buffer solutions, okay? H plus kind of depends on two things. Now that's not bad to know. It depends on the Ka for the weak acid, okay, which is where we get this pKa number from. And then it depends on the Hx to X minus ratio. So then basically what we did to get this equation, up here we would have derived H plus is equal to Ka times...
Brandy, would you please call on 26239?
Is it hx over x minus? Yes, it is up here. I don't remember. Anyway, point is, your h plus is dependent on these two things. It's dependent on your Ka value, and it's dependent on this ratio right here. So those are the two things that you need to think about when you're thinking about a buffer solution. What's my Ka value for the acid that the weak acid that I'm using? And then what's the ratio of acid to base, okay? And that's really your lab in a nutshell. Your lab is, I will give you a certain pH that you're shooting for, and you have to pick the right acid-base combination based on the Ka to get you close, and then you have to make the right concentration of acid and base in that solution to get you exactly the pH that you're looking for, okay? As long as the amount of strong acid or strong base is small relative to the amount of weak acid or conjugate base, change in pH will be small. I'm liking these notes less and less. We need pictures. I guess you've got pictures in the book, so just look at the pictures in the book. But this is also a really important point, okay? So if you think about this Henderson-Hasselbalch equation, oops, sorry. If the A minus and HA concentration in a solution are equal to one another, then A minus over HA equals 1. Everybody know what the log of 1 is? It's 0, okay? So, at that point, when you get the concentration of A minus and HA exactly equal, pH equals pKa. Which this might be making the lab that you just did make even more sense, right? Because what we did in the last lab is we were trying to get the acid and base concentrations exactly equal. And then what you found out in that lab is that at that point, the H plus concentration is equal to the Ka value. You remember that? Do you remember that? Hopefully? Hopefully? Okay. So then, okay, good. So you take the negative log of both sides of that. This becomes pH. This becomes pKa. pH equals pKa. All right, so that's where that kind of comes from. And then buffer capacity, okay? That's how much of an acid or a base can you add before the pH does start to change drastically, okay? So there's two things you have to know here. The pH of a buffer, okay, actually I said it here, okay? So the pH of a buffer, okay, pH of a buffer depends on the Ka, and it depends on the concentrations of acid and base, okay? Concentration, I guess I should say relative concentration, that's really important when you're thinking about the pH, okay? When you're thinking about buffer capacity, the amount of the acid or base that you have is the important thing, okay? So when I say relative concentrations, I'm really talking about a ratio here. And I think I have an example, and it says it right here. It depends more on the ratio than the amount for the pH, okay? I think this is going to be better if I just show you an example. So we've got a solution that is 1 molar acetic acid and sodium acetate versus a solution that is 0.1 molar acetic acid and sodium acetate, okay? So the question is, what is the pH of both of those solutions? Now we would need to know the Ka for acetic acid. I think is 1.8 times 10 to the negative. I better look it up just to make sure. .8 times 10 to the negative 5th. All right, so that's our Ka for acetic acid. So remember that Henderson-Hasselbalch equation, pH equals pKa plus the log of A minus over HA. Base over acid, okay? So what is my base concentration for the first solution up here, for this one? Base concentration is 1, right? Okay. What's my acid concentration of that first one? 1, okay? They're equal, which means this whole expression is going to cancel out, the log of A minus over HA, so pH equals pKa for that first one, right? So all I have to do is find the pKa. Now, by the way, have we talked about how to find the P of anything? I think we did, didn't we? You just take the negative log of it, right? So we take the negative log of that Ka value, and I think it ends up being 4.74. Let me just double check. Yeah, 4.74, okay? So for that first solution, the pH equals 4.74. Well, what about the second one? Can you just look at that and tell what the pH is going to be? Well, let's see. So using the same equation, we've got 0.1 molar of the acid and 0.1 molar of the base, right? So again, these are equal. So again, the whole expression cancels out. pH equals pKa. We're working with the same Ka. So for the second solution, the pH is also going to be 4.74. Well, how is that? I mean, because these are two different concentrations, right? How do they end up giving me the same pH value? Because with the, say it again. Yeah, because with the pH of a buffer solution, it's not about the amount, it's about the ratio, right? So because these are both in a 1-to-1 ratio, the pHs are going to be the same. Now, if I ask you this question instead, which one of these is going to have a higher buffer capacity? In other words, which one can I add more acid or base to before the pH starts to change? The first one, because it's got higher concentration of acid and base. Do you see the difference between those two? The difference between the capacity and the pH? Okay, so both of these have a pH of 4.74. But one of them can actually take more acid or base before the pH really starts to change. And that depends on the amount of weak acid and conjugate base you have in your buffer system. Okay? So everyone okay with that distinction between those two? All right. Oh, see, I jumped the gun on the Henderson-Hasselbalch equation, but, I mean, since we're not deriving it. Yeah, see, this is more of the derivation type stuff. Okay. So sample problem, what's the pH of a buffer that is 0.12 molar in lactic acid and 0.1 molar in sodium lactate? And then they're giving us the Ka for lactic acid. Okay? So there's two ways to solve this problem. There's the way that we talked about today in class, using an ice table. And there's Henderson-Hasselbalch. So let me show you both ways, and then you can decide which one you like better. I think I know. So on this one, you've got HC3H5O3 in equilibrium with H plus and C3H5O3 minus. Okay? And then we'll make our ice table here. The lactic acid concentration is 0.12. The sodium lactate, which that's going to be a 1-to-1 ratio, so the concentration of sodium lactate is the same as the concentration of the lactate itself, is 0.1. And then our initial concentration of H plus we can assume is 0, because we haven't dumped any H plus in there. All right? So then you do your minus X, plus X, plus X, 0.12, X, 0.10 plus X. I guess this would be minus X. But then we're going to make the simplifying assumption on the two that are the minus x and the plus x. So you end up with 1.4 times 10 to the negative fourth is equal to x times 0.10 divided by 0.12. Okay? When you work that out, x is equal to 1.68 times 10 to the negative fourth. And you take the negative log of that because the x is telling us our H plus concentration, right? So you take the negative log of that. That will give you your pH. .77. Yeah, that's right, number 6 eggs. 3.77, okay? That's pretty simple, right? So then the other way that you can do this is you can recognize, hey, this is a buffer solution with an acid and its conjugate base. So if that's the case, if it's a buffer solution, and hear me when I say this, only if it's a buffer solution. That's the only time Henderson-Hasselbalch will work, okay? Then you can use the Henderson-Hasselbalch equation. pH equals pKa plus the log of base concentration over acid. All right, so my pH is equal to the negative log of my Ka. So I take the negative log of that number. Gives me 3.85 plus the log of 0.12 divided by 0.10. Did I get those right? Nope, I got it backwards. Sorry, it's 0.12 in the acid. 0.10 divided by 0.12. And then just plug that into your calculator, and that gives you 3.77. Well, wait a second. This was 3.85, and we're adding something to it. Is that okay? Yes, that's okay, as long as this is a negative number, right? And how can you tell just by looking at that that's going to be a negative number? This is going to be less than 1 right here, the 0.1 over 0.12, so that's going to give you a negative term for that second number, okay? Which is going to mean, it means you subtract a little bit from the pH here, so you end up with 3.77. Exact same thing as you got over here. So do we have a preference? I think I do. If you have a buffer solution, use Henderson-Hasselbalch. When you are taking the AP exam, you need to save yourself time, okay? So this is a good way to save time. Use this equation. But you've got to recognize when you can use it and when you can't, all right? Okay, so an alternative solution. I had that set up for that. How many moles of NH4Cl must be added to 2 liters of a 0.10 molar NH3 to form a buffer whose pH is 9? Well, see, that's just unnecessary. This one's basically just a let's plug and chug and figure out different ways that we can ask questions about Henderson-Hasselbalch. I don't think you're going to probably see one like this. Let me skip ahead and see what else we got here. Oh, you know what, though? I know we're not going to see this because they specifically said, here's one of the exclusion statements. Oh, boy. But then you need to know how to do this for titrations. That's interesting. I hadn't thought about the ramifications of that particular exclusion statement. So a problem like this, what they're telling me in the exclusion statements, sorry, I'm talking to myself a little bit here. They're saying on the new AP curriculum that you don't need to know what happens when you put strong acid or strong base into a buffer solution. You don't have to calculate the new pH. which means all of this should be unnecessary, in theory. Now, what I don't quite get yet is what kinds of questions they're going to ask you about titration, if they're just going to be conceptual, because that's essentially what a titration is. During titration, you basically create a buffer solution, and then in the middle of creating that buffer solution, now you're adding a strong acid or a strong base to the buffer solution, and then you change it until you've used up one of the buffers, and then that's why you get that, you remember in the titrations that we did earlier in the year, how you get this, slight rise in pH when you're adding base, and then all of a sudden it spikes like that, right? Basically what that is, right here you've got a buffer, okay? So you're adding an acid to a base, right? So you're adding acid to this base. The base is reacting with the acid, resisting the pH change. As soon as you use up all the base, right about here, see, I'm saying this backwards, because if you're, let's say you're adding base to acid, okay? So you're adding the base. As soon as you've used up all the acid, now the pH is just going to shoot up, because the only thing you're doing now is just you're dumping a bunch of OH minus into that water, okay? And there's nothing to react with it anymore. It's just a bunch of OH. So that's why these titration curves happen the way that they do, which we'll talk about in the next section. But what I don't think that you'll need to know is how to do the actual calculations for this. I think you'll need to know it in theory. Now, you might need to know it in the context of the titrations. I've got to go back and check the AP curriculum for that. But for the buffer solution section, we don't really need to talk about it. So what you need to know for the buffer solutions, since we're getting close to being out of time anyway, you need to know how a buffer solution gets created, adding an acid to its conjugate base, okay? You need to know what two things affect the pH of that buffer solution. That's going to be the Ka of the acid, and then the ratio of the acid to the base in that solution, okay? And then you basically need to know how to make a buffer solution at a certain pH, which we'll practice that when we do the labs, so you don't have to worry about that yet necessarily. And I've got a bunch of practice problems I'm going to throw at you tomorrow that will kind of extend this idea. But really, if you know how to use Henderson-Hasselbalch, I think for most of what we're doing in the buffer section, you're going to be fine, okay? And then we'll just deal with the titration stuff when it comes. All right, I'll see you guys tomorrow.